Okay, so just sort of a quick review here. The phi equals mav formula. This part over here is referred to as the impulse, or J.
And that's the momentum.
And this one is the change in momentum, delta P, right?
Yeah.
And when we increase the amount of time that we apply a force, we get a greater velocity. So that's kind of the very quick review from all that, right? What if you've got, and now I'm on page 283 here. I've got a force versus time graph. So when it says force versus time, anytime it says something versus something, the force is always up there, and the second one is always down there. You can, yeah. This is sort of a continuation from the other day. In most cases, the force acting on an object during the collision process is a complicated one. It increases as the colliding objects are compressed together and decreases as the forces move away from each other. Most force versus time graphs are not nice, beautiful, straight lines, right? The force is not the same all the time. All this can be seen at a microscopic level for hard objects. We're going to use average force when dealing with such interactions. We can still get a value for the impulse if we have a graph of force versus time available to us. Analysis of the graph in figure 8.14a shows that the area under the graph produces the desired units of impulse. Okay, so what they're saying there is, because force is measured in newtons, and time is measured in seconds, when you take the area here, well, that's going to be newtons times seconds, which is equal to impulse. Right?
Oh my God.
Which means that this area here, the area under the graph, is equal to the impulse, even when the force is not constant. Okay? Even when the force is not constant. So, as a quick example there's that figure 8.14a, they've got a graph, and it's kind of triangular, right? Because as you kick the football, the force increases as it compresses, and then as it decreases as it expands. So the force goes up like that, right? So you could look at it two ways. You could find the average force, F bar, I guess, or you could find the area under that. And because it's a triangle, in this case here, we would go area equals 1/2 the base times the height. Now, can we actually see numbers there?
Identical triangles, then you don't have to do that. You can just go based on height.
True enough. I guess it depends. You would only go. When I was thinking base, I was thinking all of that and height, all of that, right? Yeah. Yeah. So in this case here, it's going to be 1.2 times 25. Right? So that would be 15 Newton seconds of impulse. And if you know the mass of the ball, well, then you can figure out the change in the velocity and then the acceleration, and you can figure out how far it goes and all that fun stuff. Kind of thing, right? Okay. What if it's not nice like that? Right? Just give up. Calculate the impulse for the time interval shown in each of the following graphs. This is example number 4. Now, example number 4, the first graph is like this. Right? And it starts at 70. And it ends at 20. Over a time of conveniently 1 second. So what is the impulse equal to? We're talking about area. Right? So it would be rectangle plus triangle in this case, right? So it would be, let's do the triangle first, 1/2 the base times the height, plus the base times the height, I guess we could say. 1/2 of 1. The height of just the triangle is from 20 to 70, which is 50, which is going to be 25. And then the rectangle part is base times height, so that's going to be 1 times 20, it looks like. Whoops. 1, 20. So here the impulse is 45 Newton seconds. Okay? So it's also fairly doable when it's a nice straight line kind of geometric shape. But what do if it's all kind of curvy?
Oh no! So there would be a.
Now
now it's time to give up.
Yeah.
When's that time?
What do you do if it's all kind of curvy? Because let's face it, in real life, things like this tend to be curvy.
Like average.
The answer,
Use? Calculate. No.
the answer is use calculus.
Done, Mike, get up.
Who's in advanced math? Anyone? Just you? Oh yeah, this is the lunchtime, right?
Yeah.
Who teaches that? Oh, okay, yeah. Mr. Legoski. Have you done Have you? Yeah, I can go with that. Video conference. Have you done integration yet? No, you have. He hasn't shown you anything like this, where they draw like boxes like this.
I've seen that.
Yeah.
Oh no, don't do that. It's gonna be so hard.
Okay. Okay. So this is the basic idea behind integration. Okay. Is the following? Let me just see if I can zoom in here. I didn't draw this very well.
Oh God.
We're gonna have to do like, oh, you know, is that like a lot of work? And you have to like do each one, like math for each one?
Yeah.
There's
Well,
like 50 boxes.
I'm not going to teach you calculus, but I'm going to give you a little calculus intro, and this will be good for you too, Adrian. Okay. The basic idea is this, is if you make these bars, these columns, small enough. Like first of all, I guess before I even do that, right? Let's talk about if I consider each one of these columns as a rectangle, and I'm finding the area, I'm a little bit over here, right? Like that little bit there isn't really area under the curve, it's kind of over the edge kind of thing, right? Okay, but conveniently enough, and I didn't draw it very well, but that little bit right there is kind of almost the same as that little bit right there, which is the opposite, right?
So it evens out.
It's kind of under, it evens out. And if you make the columns small enough, the amount that you're over and under are practically equal to each other, as long as you make those columns smaller. And that is a key idea under integration, which is the opposite of derivatives. For you guys, all you really have to do is count the squares. That's all it really is. Okay? So you could learn calculus. You can see a picture there on page 285. There's a little bit there. Right? You can see the under the curve, there's the green sort of bars, and you can see that some are under and some are over and so on, right? And then there's the alternate solution. And I'm just going to write this out because it'll remind me of my calculus and make me feel smarter. Okay? So it's divide the graph interval into n subintervals, each of duration delta t over n. Assuming the force is constant for each interval at f average, the total impulse is the sum of the areas. If we divide the 0.7 interval into 7 1/10 of a second intervals and so on, the total impulse is blah, 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 and it gets smaller and smaller and smaller. And it's actually written like this. J is equal to the integral between T1. Oh, I'm zoomed in here, aren't I?
Stop it.
You don't actually need to know this. Integral between T1 and T2 of f dt. You actually need to use calculus to do this. You would actually need to know the equation of that curve. Now, the equation of that curve is going to be pretty crazy, right? It's a bell curve. But if you had just a plain old x squared, right, then using integration and calculus, you can actually figure out the area underneath. It's actually relatively simple. If I showed you the math, you go, that's it? I'm not gonna, because I kind of make sure that I'm not really 100% sure I know how to do it. It's been so long. Okay? But for what I'm saying is that if you've got a curve like this, all I want you to do is count the squares and sort of estimate. That's all. Not good.
Squares. We start on squares?
Yeah. Well, I mean, it'll probably be on graph paper, right?
Okay.
Yeah, it'll be on graph paper.
Well, we're going to get some example questions, right?
There's a couple I know in this set, but really all you got to do is be able to count. Now, in the book, there are some questions on page 286. 4, 5, and 6. Page 307, oh, there's a whole whack. 29, 31, 36,
What's that now?
37. These are all equation or graph ones, I think. 42, 47.
No, it's not. This is 4A, finding and
307. Let me just check here.
following situations. 20 kg object in velocity from 0 to 3 meters per second. That's fat now.
307. These all fat nav ones?
4 is
Oh yeah.
5.
29, 30. Yeah. So those are all. Most of them are fat nabs. I'll tell you which ones are the graphs.
6 is a graph.
6.
6.
Mike, I'm getting sick of you talking.
2876 is a graph, Sean.
I think it's just number 50 that have graphs, right? It's just 50 that have graphs. In how come I haven't said, you know what? These are all, let me just do this. These are all fat nav, and these ones here, 50, 51, these ones are all graphs here. Right? Okay. So, should I give you time, do you think, to try a few of these
Yeah, give us
graph
some
ones?
time, they can teach us. And we'll just screw up after 5 seconds.
All right.
Because that's what happens to me.